Hello everyone and welcome to this lecture. In the last lecture we have started discussion on signed graphs. We have in particular asked about the balanced sign graphs, unbalanced sign graphs. There was a very nice theorem on balanced sign graph, right, in terms of the eigenvalues. So a signed graph is balanced if and only if the eigenvalues of its signed adjacency matrix are same as the eigenvalues of the underlying unsigned matrix or unsigned adjacency matrix, right? Okay, very good. So now let us move the discussion forward. Today we will learn one concept, and this concept is of signed switching. Okay, signed switching in signed graph. Okay, signed or maybe just switching in signed graph. So maybe signed switching. Signed switching. What we mean by this in signed spelling mistake signed graphs. Okay, so what you do, suppose there is a signed graph GS. Okay, so GS is signed graph. Okay, the bigger one. Okay, you pick a subset. So suppose this is subset U. Okay, now what you do, whatever the edges that are going, maybe some will be negative edges, some will be plus edges. Okay, you change the sign. Okay, so now after that what the sign will be, so let me actually color with it maybe some different color. Okay, yeah, maybe this one. Okay, so now this is dotted one. Now this will be fully dark. So basically now it will become positive. These are the dotted ones. Okay, so this is the signed one. Okay, so now first result that we will prove is that the signed switching, once we do basically the signed switching, the resulting graph still have the same eigenvalues. Okay, so let me actually denote this original graph by GS, and after the signed switching with respect to some vertex subset, so suppose this graph is T. Okay, so we will prove that the eigenvalues of GS and GT are same. The eigenvalues of GS and GT are the same. How to prove this? This is actually very straightforward. We have seen the technique that I will show many times. Okay, so let us go ahead with this. Okay, so if you look at the adjacency matrix or maybe the signed adjacency matrix of GS, okay, and now what could be basically this? How can you write the signed adjacency matrix of GS in terms of its signed some switching, right? And by the way, so let me actually first write it. Okay, so if you see that this matrix can be obtained from this by multiplying a suitable diagonal matrix D. Okay, suitable diagonal matrix D on both end side. Okay, both side of AGT. Okay, what is this D? So D is nothing but is a diagonal matrix. Now maybe you now realize what will be the structure of diagonal matrix. Diagonal matrix. Okay. So basically, whenever this I is so D, where diagonal matrix, where the ith entry, okay, the ith entry is -1, when I belongs to U with respect to which this switching is done. Okay, with respect to, basically if you see that, so let me actually write it separately. So this is U, okay, and this is V minus U. Okay, maybe I will write it. So this is V minus U. Okay, so these are actually here the switching is done. So some edges it will be positive, some minus. Okay, the switching here, so just flip the basically sign. Okay, so in this way, if you see that, this is very easy to see. And when I belongs to U, why this is true? I mean, this is very simple definition. If you see the structure of AGS, right? So there will be this part, right? So this is, maybe you can call this is U matrix. Okay, this is V minus U. Okay, so whatever the matrix related to, maybe you can call A here, A of this, right? And this is the edges which are going from U to V minus U. Okay, and this once you do with minus, so suppose this is corresponding to U, right? And this is V minus U. Okay, so this is plus, so this is minus actually, minus. Okay, dot -1. Okay, and similarly you do here, right? Okay, so these things will be unchanged. The only change that will happening will be here. So here +1 will become -1. So -1 will become +1. Okay, so on. Okay, very good. So now this is very straightforward. Now AGS GS is nothing but D A G T. Okay, D. Now the things are we have already seen multiple of times that these two matrices are similar. Okay, so they have the same eigenvalue, the same eigenvalues. Okay, same eigenvalues. Very simple. We will make very beautiful use of this this small result very shortly. Okay, has the same eigenvalues. Very good. Now the next result is, okay, the next result is actually about comparing the largest eigenvalue of signed graph, okay, with its signed unsigned version. Okay, basically the simple unsigned graph. Okay, very good. So theorem, let GS be a signed graph, signed graph, okay, and maybe let me write, and GB its underlying unsigned graph, basically undirected simple graph, okay, unsigned graph. And what do you think the largest eigenvalue, what will be the relation between the largest eigenvalue of this graph? Okay, then the largest eigenvalue, let me call it lambda 1 of GS is less or equal to lambda 1 of G. Okay, how to prove this? The proof is very simple. Again, the Rayleigh quotient we will take. Okay, so suppose proof. Okay, so suppose maybe you can say suppose X is unit eigenvector of GS, okay, of GS. Actually here we mean the sign adjacency matrix and the adjacency matrix. Okay, so maybe you can call AGS here and A here, simple. Okay, so unit vector of AGS is a unit eigenvector of A for lambda 1, okay, for the eigenvalue lambda 1. Then we know that then actually this is nothing, so let me write it lambda simply by GS. Okay, so simply GS, so it's actually nothing but this, right? X transpose A AS. I will write now simply AS actually. Okay, I mean, because I mean this is too complicated, otherwise it will become let me write here GS only, but here now onwards, so AGS is same as, so let me write AGS is actually same as AS. Okay, X transpose X. Okay, very simple. Now if you open this is nothing but 2 times all the edges. So xi, xj, but there are 2 types of edges. One edges are basically some edges are plus, some edges are minus. So this will be what? So I and j, but some edges are with plus, minus, some edges which are negative. So the term will be basically the sign will be negative, right? So minus. Okay. Now if you see that this quantity is always less or equal to this quantity, so let me actually take mod of this xi, xj. Okay, this is mod, sorry, and let me put xj. Okay, very good. And then yeah, of course I positive, then same I can do here I j, and this again is negative. Okay, and then what? Now I can write this as this, right? So this is nothing but mod x a mod x transpose. Okay, and this is equal to what? This is equal to lambda 1 of a. Very simple, very simple. So we have proven that. Okay, so this is now very straightforward. So the lambda 1 of GS is always less or equal to lambda 1 of G. Okay, lambda. So this A is actually nothing but adjacency matrix of G. Very simple. Okay, now let us see one more beautiful theorem on balanced graph just by looking at the largest eigenvalue of signed graph and its unsigned version can be determined the graph is balanced or not. Remember, in the last lecture we have seen if all the eigenvalues are same, okay, then and only then the signed graph will be balanced graph. But suppose the connectivity is, suppose the graph is connected, do we really need to look at all the eigenvalues? Okay, so we will prove it here. So the theorem is this. Okay, let GS be a connected graph, a connected signed graph, okay, signed graph, okay, then okay, then GS is balanced if and only if, okay, lambda 1 of GS is same as lambda 1 of the underlying unsigned graph. Okay, very good. How to prove this beautiful claim? Okay, so proof. Okay, so one direction is very easy. So suppose GS is balanced. If GS is balanced, we have already seen this. If GS is balanced, then all the eigenvalues of GS and G are the same. We have proven in the last lecture. If then what? Then lambda 1 equal to lambda 1 of GS is same as lambda 1 of G. Already proven in the last lecture. Very good. It's straightforward. Okay. So now let us do the converse part. Okay. So now let lambda 1 of GS is equal to lambda 1 of G. Okay. Now again let us assume, so in proving this, okay, so we will assume that there is some unit eigenvector of lambda 1 of GS, okay, and then we will see that what will be the relation to lambda 1 of G. Okay, so suppose, so let X be an unit eigenvector, I would say, eigenvector of lambda 1 of GS. Okay, now we have seen just now only, if this is the case, right, so there is everywhere equality. That means there is everywhere equality. So let me actually write it again. So that means this is what? So X transpose, I would say A of S, X transpose S. This is nothing but lambda 1 of GS. Okay, and so this is giving. Actually, this was. So let me write it quickly. So so when I and J, these were positive, and then this was giving IJ. Okay, then minus of IJ. Okay, xij summation, and this was the case when there was negative edges. Okay, and then we have proven this that this quantity is always equal to this, right? Mod this and then A of this. Okay, which actually is less or equal to lambda 1 of A, or I mean just G. Okay, but we know that these quantities are same. We know that this quantity and this quantity is same, right? So that means everywhere there is a equality. Everywhere there is an equality, right? There is equality. Okay, now this implies that mod X is an eigenvector of lambda 1, right, of lambda 1 of G. And by the way, since graph is connected, none of the entries here is 0. Now what next? Now next, consider the vector X. Okay, vector X, remember vector X is what? Eigenvector of this, right? So let me actually again write. So vector of S is this, right, times lambda 1 of AS. Okay, lambda 1 of AS times X. So this was the eigenvector. Okay, now let us perform a signed switching. Let us perform a signed switching with respect to let me write it clearly. With respect to the vertices, whose indices, whose actually entries, whose corresponding entries in X are negative. Okay, so basically wherever this X is negative, right, you choose those vertices. Okay, and then do the signed switching with respect to that subset. So subset of those vertices. Okay, subset consists of those vertices rather. Okay, okay, let the resulting graph be, let the resulting signed graph be GT. Okay, and we already know in that case what will happen. So there will be actually this, right? So AS is actually, let me write here AGS now. Here AGS is nothing but some matrix here D, right? Diagonal matrix, and then this AGT D. Okay. Now next, this implies that we have seen the eigenvalues of those will be same, right? Both the matrix will be this. Further, what about the eigenvector? The dx is an eigenvector, very easy to see, eigenvector of actually AGT for lambda for lambda 1 of AGT, you can say now, because AGT, the lambda 1 of AGT is same as lambda 1 AGS because the eigenvalues are same. Okay, so lambda 1 of AGT. Okay, for lambda 1. Okay, very good. Now, but if you see that dx is what? Dx is what? Okay, so dx is nothing but mod x, right? Because d we are choosing that such that they are negative corresponding to those. Okay, and we are also switching with respect to negative entries, right? So that means this is this. That means what? Now this implies that using this theorem, this proof that in GT there is no there is no negative edge, right? Otherwise this will not be positive. There is no negative edge. Okay, which in further implies that GT is actually isomorphic to your unsigned version. Okay, isomorphic to G, and G has, by default G is balanced, right? This implies that further GT is a balanced graph. GT, or maybe GS is balanced. G is balanced graph. Okay, so very good. Okay, because this is actually, these two are signed equivalent. So if this is balanced, this is also balanced. Okay, very good. Okay, so thank you very much, and see you in the next lecture. Yeah.